Hello and welcome to the Newton's third law video tutorial. Here we're going to see if we can get a deeper understanding of Newton's third law past just being able to regurgitate for every action there's an equal and opposite reaction, because it's, as most things, it's a lot easier to say that, a lot harder to understand what that actually means. So in our first question here, we've got two weights, a 10 Newton and a 4 Newton weight attached by a string, and we're going to see if we can figure out the tension in that string. Here are our answer choices, and we've got, looks like we got 4, and we've got 10. We've got 6, which looks like the difference between them. 7, which is, I guess if you add them up and then divide by 2, you get 7. And so you said it's the average. And then 14, just the sum of those two. So here's the idea. This weight here is going to pull no harder than this weight can pull on the system. So, or the 4 Newton weight is pulling on the 10 Newton as hard as the 10 Newton is pulling on the 4 Newton. So this one can't pull any harder than this one can. So you can imagine this weight is pulling on that molecule in the string with 4 newtons, and that molecule is pulling on that one with 4 newtons, and so on and so on and so on until you get to this. So really what you're looking at is, let's see if we can draw a little diagram. There we go. So that's the 10 Newton pulling down this way, and you've got the 4 Newton pulling up that way. So the 4 Newton is pulling on the 10, and the 10 Newton looks like it's going to be pulling stronger, so that's just going to cause downward acceleration. Downward meaning this one will go down. So the whole system should accelerate down that way. But the tension in the cord is going to be equal to the smaller of the two, the 4 Newton. The way to think of it is this extra amount here is being translated into acceleration. And as far as what are the forces acting on the string, it's going to be this 4 Newton force. So we've got the 4 Newton force acting on the string. Another way to think of it is, let's bold that whole thing. Another way to think of it is this one can't pull any harder than this one can. So it's kind of limited by the 4 Newton force pulling up, this 4 Newton force. So here's our next example. We've got, this time the weights are the same. So this one is going to pull with 10 newtons, and this one's going to pull with 10 newtons. So the way to think of it is this guy here will be pulling with 10 newtons, and this one can fight back with 10 newtons of force. So 10 newtons is the tension in the cable. It's not 20. In order for it to be 20, well, let's say if we change this to 20, if that gets changed to 20, then the tension is still 10 newtons, because this one can only fight back with the 10 Newton force that this one's being applying to the system. So in order for it to be 20, they both have to be 20. So this is going to be 10. So they're both pulling on the cord with 10 newtons. This one's pulling 10 newtons and the cord pulls back with 10 newtons. It's almost like you can think of the entire system just being right here, because whatever tension you have in the cord at one spot will be the tension everywhere in that cord, because it's a chain reaction of each molecule pulling on the next one. Okay, let's do another question, see if we can get to understand what's going on. So here we've got a guy pushing on a box with 1,000 newtons of force, and the box is not moving. So what can we say about the force the box is pushing back on the man with? So if he's pushing with 1,000 newtons, then Newton's third law says that the box is going to push back with 1,000 newtons. This seems like a pretty easy question. In fact, all these questions are easy because they're always just the same answer. But now let's see if we can make sense of this. It seems like maybe this might be the right answer. The force is greater than 1,000 newtons because the box is not moving at all. So the box must be pushing back harder. But what's really going on is that there's other forces here. There's friction between the box and the floor, and there's friction between the guy's feet and the floor. So the reason why the box is not budging is because the friction between the box and the ground is greater than the friction between the feet and the ground. And those don't have to be equal because they're not an equal and opposite pair. It's not box on ground, ground on box, or man on box, box on man. It's box on ground, man on ground. Those are not a pair. So That's why the box is not budging, because there's other forces involved. All right, for our last example here, we've got a guy doing a clean and jerk lift, and here's the question: for every force there's an equal and opposite force, then shouldn't the bar be pushing on him just as hard as he's pushing on the bar? And so how does this even move? And that's a common issue with these problems, is when you really think about it, how does anything ever move if the forces are always equal? So what you got to realize is that the thing that's bringing the bar down is not him, it's gravity. So this force right here is the earth pulling down on the bar. So this force, let's move it over here. This force is earth on bar. All right, so that's the down force on the bar. The up force on the bar is the man pushing up on the bar. So if this was earth on bar and bar on earth, they would have to be equal. If this was man on bar and bar on man, those would have to be equal. But it's not. It's the earth on the bar pulling it down, and it's the man on the bar pushing it up. So if this force is larger than this force, then the bar will accelerate up. The key idea here is that the equal and opposite reaction thing is for, it's like if you push on a wall, the wall pushes on you the same. It's got to be the object pushing back on whatever was pushing on it or pulling. This is one thing on the bar and a different thing on the bar. And so those are not an action-reaction pair. And so the bar can accelerate up because the forces don't have to be equal. Thank you for watching the Newton's third law video tutorial.